Okay. Hello. I'm. By now, you should have opened up the Molecular Polarity um, webpage. You should have downloaded the Molecular Polarity worksheet, and you should have gotten an example. Okay. You by now you know the fact that you have bond bond polarity, which is the distribution of electrons through between two atoms, and molecular geometry. You're going to use both of those, and what we want to know now is are the electrons evenly distributed throughout the molecule, which if it is, it's called nonpolar molecule, or are they unevenly distributed, i.e., are there a region where a lot of electrons are located or going towards, partially negative end, and a region where the lack of electrons, partially positive end, creating two different regions, two different poles, and it's called a polar molecule or basically a dipole. And those are the only two possibilities. Okay? And if you had to guess, and that's what the notes say, you're always going to guess unevenly distributed electrons. So that's why I'm going to make you memorize assume polar, prove nonpolar. So you're going to go into the substance and thinking it's unevenly distributed, and you're going to prove to me that it's evenly distributed. So how do I know that a substance is evenly distributed? By the geometry and by the bond polarity. And there's only two possibilities. The first possibility is all nonpolar bonds, and the geometry doesn't make a difference. So if all the bonds have the electrons evenly distributed through them, then the molecule must be evenly distributed. And there's an example of the type in the notes. Or the other one is it's a polar bond, so unevenly distributed in the between the two atoms. However, due to the geometry of the molecule, it's called symmetry. Then the looking at the overall substance, the electrons are evenly distributed, and that's the only two possibilities. So we're going to go to our handout. Here's an example of the handout, and in this case, a row is what one question is. This is your bond polarity block, so you got to fill that in. And if you have more than one type of atoms bonding together, you need more blocks. So you go over here. And this one here is for your Lewis dot structure, your molecular geometry / molecular polarity information. So I have an example here. Okay, and this is and these are three possibilities. So the first one is CH4. C to H is the bond. Okay, 2.5, 2.1. You have 0.4 nonpolar. It's a nonpolar bond. Here's my Lewis dot structure. So the first line is the line people make mistakes on. It's asking you for the bond polarity, not that it's a single, double, or triple bond. So in this case, you have nonpolar bonds because that's what that block tells you, and you have 4 of them due to the Lewis dot structure. Okay, the geometry is tetrahedral. In parentheses, you tell me if it's that geometry is symmetrical or not. So you'd write not sim or sim. That's a symmetrical molecule. So the answer question: polar bonds cancel out. Okay, you circle yes if their polar bonds cancel out. You circle no, N for no, they don't. And the line is for this application, Na. There are no polar bonds. You write Na. Okay, so that's usually only time you write anything in the line. So therefore, we have a compound or a substance that has all nonpolar bonds. If it's all nonpolar bonds, even though the shape is symmetrical, it doesn't make a difference. It's nonpolar. It's a nonpolar molecule. And then from the video on into molecular forces, what you figure is all nonpolar molecules or substances exert what is called a London dispersion intermolecular force. Again, you figure that out next video. The next one is when you have polar bonds. So CO2 is C to O, and you can see that it's a polar bond. You have a little polar symbol. And here's your Lewis dot structure. And now you show the symbols of the polars, two polar bonds, so you show two polar symbols. You have two polar bonds. Now the geometry is linear, and linear is a symmetrical molecule. And how do you know it's a symmetrical molecule? You go to here, and it tells you which is the symmetrical molecules. Right here. Right in there. Okay? And linear is 1, so it is symmetrical. So what happens is, do the polar bonds cancel out? Yes. So you can just simply circle Y. Yes. So you don't have to write yes. You can circle the Y. So even though the bonds are polar, it's a nonpolar molecule. Therefore, again, you have London dispersion forces. I abbreviated it. And then the last one is NH4. Again, it's a polar molecule. Here's my Lewis dot structures, 3 polar bonds. Now the geometry is pyramidal. Pyramidal is not symmetrical. And if you look, what you see is that those arrows mean the electrons are going in that direction. So you have a region of a lot of electrons, top of the pyramid, and a region of the lack of electrons, the bottom of the pyramid near the H's. So you create two different areas, so therefore, do the polar bonds cancel out N, or circle N, or no? Therefore, it's a polar molecule, it's a dipole, and for this particular type of dipole, it has a special intermolecular force name called hydrogen bonding. Okay, so that's how you do it. So again, we're trying to figure out if it's a polar molecule or non-polar molecule, because we're looking now at the whole substance and not just in the parts of it. Okay, I hope that that